So what is the point of A star search? It's because uniform cost search uses too darn much memory. And it searches too much of the space, and we want to use less memory and search less of the space and still be optimal. And the only way it accomplishes that is by using a heuristic. Right? With me? Okay. That's one problem with uniform cost search. What's another problem with uniform cost search that we mentioned before? Yeah, so A star needs a heuristic. That's kind of a problem with A star search, is heuristics are not very general, because if you find a heuristic for some problem, it's not going to work for some other problem, necessarily. So this is a big deal. You might say that uniform cost search is far more general than A star, because A star requires domain knowledge to use. Uniform cost search will solve any problem in general. But uniform cost search uses too much memory. Truthfully, A star search uses too much memory too. I say throw them both out and never use them, because they're not good enough for real hard problems. And I like the really hard problems. Another problem with both of these algorithms is neither of them handle uncertainty. Right? They're both assuming that you can tell the future. If at some point I take this step, here's exactly what will happen. What happens if you're in a future where you're in a problem or a game or a life where you do an action and you don't know for sure what the consequences of that action will be? Might be this, might be that. Can you operate effectively in that environment? Well, you're a human and you do. So intelligent things can, therefore intelligent machines should be able to as well. Will you buy that? I claim that operating in the face of uncertainty is a fundamental property of intelligence, and these algorithms don't do it at all. So let's get rid of them, and let's talk about how to handle uncertainty. That'll be kind of the topic for right now. Let's suppose that you wake up one morning, you're laying in bed, and you smell bacon. And you think, bacon. Right? That happened to me today. Except it wasn't when I was waking up, it was when I was walking to class. Somebody was cooking bacon inside one of the frat houses, and man, I wanted to be in that fraternity at that moment. Let's suppose while you're laying in bed, you think to yourself, well, 60% of the time, my mom gets up and makes bacon. And 40% of the time, my dad goes downstairs and makes bacon. Who do you think is making the bacon? Probably your mom, right? Because your mom cooks most days and your dad cooks fewer days. And this is just an arbitrary example. I'm not trying to imply every family needs to have these two situations or anything like that, so don't take this the wrong way. And I'm not trying to suggest moms should cook more than dads. Okay, we're switching it just so I can have a little bit of political correctness here. Dad cooks 60% of the time, and mom cooks only 40% of the time in this particular house. Okay, and there could be a grandma living with you too, but whatever. So, which is the more rational belief? Dad is making bacon or mom is making bacon? Obviously now it's dad, because he has 60%. So, is it truthful to say you know dad is making bacon? No, because 40% of the time mom makes bacon. You do not know. So, consider these three hypotheses. 1, I know dad is making bacon. That's just not honest. By the way, have you ever noticed that you fry bacon and you bake fries? Isn't that just wrong? Okay. I mean, you can also deep fry fries and then they end up better, but the kind you buy at the store, you stick in the oven and you just, what you baking? Fries. What you frying? Bacon. Okay. Number 2, I know mom is making bacon. Making bacon. Bacon. Okay. And number 3, I 60% believe that Dad is making bacon, and I 40% believe that Mom is making bacon. You get my point. The third option here is driven by the data, and therefore is at least consistent with the data. The other two options are not consistent with the data. They're snapping to the nearest extreme. And what a lot of people don't seem to realize is you can not know the truth. It's okay to not know everything. You can actually represent your beliefs with some kind of a distribution, meaning you can say, I this much believe hypothesis A, and I that much believe hypothesis B. There's no rule in the universe that says you have to take 100% of your confidence and throw it behind one hypothesis. And yet, it's this nasty habit that humans have. They seem to think they have to believe something 100%. And humans have a very strong tendency to put way too much confidence on something when they see a little bit of evidence to support it. Have we seen any evidence to support that Dad is making bacon? Yeah. Well, we have prior evidence, right? Do we have any evidence to know that he's making bacon today? No?
No. Evidence that bacon is being made.
Yeah, there's evidence bacon is being made. So we know one of these is occurring. Okay, well, what if you look out the window and you see Mom driving off in her car? Now, all of a sudden, the Dad hypothesis grows bigger and the Mom hypothesis grows smaller, but there's still a slim chance that she started the bacon and then drove away for some emergency and forgot to turn off the stove. I don't know what. You really shouldn't ever say with 100% certainty, I know Dad's making bacon, until you've gone downstairs and see Dad baking bacon, then there's pretty much not much chance left for Mom anymore, right? Okay. This is, well, we're kind of delving into a little bit of math here. Does anybody remember statistics? You had to take a stats class before you took this one, right? Has anybody not taken a stats class at all? Awesome, good. Well, this is a probability distribution. Percent kind of means divide by 100, so I'm going to change these numbers to say 0.6 and 0.4, because that's more the stats way to do it. And now these numbers always sum to 1, and when they sum to 1, then it's a probability distribution, right? This particular kind of distribution is called a categorical distribution. There are other kinds of distributions, but in a categorical distribution, you have some number of categories. No pictures to use? There's a picture. Well, as it happens, the probability on a categorical distribution will always form a simplex because it must sum to 1, and there's an example of that. But the point of a categorical distribution is you have some number of values, and they all sum to 1. Each value could represent a hypothesis, and so a distribution over possible hypotheses kind of forms beliefs, does it not? Okay. Well, let's do an example of how we can use uncertain beliefs to make intelligent computations. Let's suppose that you're going to, a new lottery comes to town. Should you participate in the lottery? No. Good answer. Your parents raised you well. Let's suppose that there is a 1 in, I don't know, 10,000 chance that you could possibly win. And it costs you $10 per ticket. And if you win the lottery, you get $1 million. Should you participate in this lottery? Yeah. Okay, I've heard both yeses and I've heard nos. Those of you who said no, your parents raised you well. Of course it's a trick. Of course they're scamming you somehow. You should not participate in lotteries because it's stupid. However, let's pretend that we don't have any prior experience and that the universe actually is correctly represented by these numbers. Okay, so there are no bad people. There's no such thing as evil lotteries. It's just these numbers are the whole truth and nothing but the truth of the way the universe works. Now should you participate in this lottery? So let's do a little utility theory. There's two possibilities, right? If you could participate, well, let's put it this way. You could participate, or you could choose not to participate. Don't. And if you participate, you lose $10. Right? And if you don't, you gain $0 and lose $0. We'll just say 0. Nothing happens, right? And I know you already know how to do this, but I'm going to do it the very slow and painful way because I want to formalize how we do this so that you can see how to do it with harder and harder problems. Okay? If you participate, there are two things that could happen. There is a 1 in 10,000 chance that you will win, and if you win, you get plus $1 million, right? And this detail I've already put right there, so get rid of that. And what happens if you don't win?
Nothing.
You get plus $0. And maybe if we're considering more than just the cost, if money is not your only objective, maybe there's a little bit of frustration that comes with losing. You could even say that the anger that comes from you for not losing has so much probability of causing a heart attack, and then that would cost so much at the hospital. Or maybe the anger is worth to you something like 1 cent. At least now we're accounting for everything. Well, what is the utility of not participating in the lottery? Nothing. You get to keep your money. What is the utility of participating in the lottery? Well, think about it this way. Imagine if you took the universe, and we'll go into a multiverse voodoo for a minute, imagine there were 10,000 universes. How many of these universes would you win the lottery in? Exactly one of them, right? Because we're doing non-determinism now. Well, if you won the lottery in one universe and you lost it in 9,999 universes, then you could imagine that you paid $10 times 9,999, and you paid $10 and won $1 million, right? And now we've summed up the utility over all of these 10,000 parallel universes. And since you only get to live in one parallel universe, let's divide out the 10,000. And that will tell us on average how good it is to participate in the lottery.